Well, hello everyone and welcome back to Adrian's Digital Basement. On today's video, we're going to do another Commodore 64 repair, but I'm going to be doing it not with my normal bench oscilloscope, but another one of these inexpensive oscilloscopes from AliExpress. This one is called the ZEEWEII DSO1511G, and I paid a total of $57 for this. As you can tell by the little case here, it's a little portable thing, but it has some interesting tricks up its sleeve, which might make it an interesting choice if you're looking for one of these small scopes. So, without further ado, let's get right to it. Before we get started, I just want to mention that, as usual with my repair/scope review videos, I'm going to do the scope review first, but if you want to skip ahead and just look at the Commodore 64 review, click the link in the description below, the time link, to jump to that. I will be using this scope to do the repair, but before we dig into that, I just want to see how this thing works. Well, I might not be using it for the repair if it's kind of useless. All right, so the ZEEWEII little portable scope. Let's pop this out of the little carrying case it came with, which is kind of nifty. It's got a rubbery coating. There it is. I haven't actually done anything with this other than take it out and give it a quick charge, so it was fully charged for this video. I have the ZIF64, which of course is in this VIC-20 case, hooked up to my PC capture device just to make sure that all of my capture stuff is working. I don't want to go and try to troubleshoot a computer to have my capture system be the problem, which is tricking me into thinking that the machine's not working. Let me move the 64 out of the way and let's take a look at this little scope here. So I've had this scope for a little while and I paid $57 total, including shipping. But the funny thing is, if we look here, there it shows $57.99 as the price, but then there it shows $114.80 as the price. And I don't know what's going on here. Both of these have that higher price. So I'm not sure if there's like a shortage right now or something else is going on, but it is odd that $57.99 is literally on the picture of the device. So I'm assuming that by the time you watch this video, perhaps it'll be back to that price, or maybe we have to use a different seller. Now you see some specs on the screenshot there. Let's ignore those because I'm not so sure about the validity of those. As I had mentioned, the carrying case feels decently nice. It's already getting a little scuffed up or whatever. That was not like it when I got it, so oh well. So here's the scope, and it's really, really little. There it is, and let's just compare it to a Commodore 64 cartridge. You can see that they're basically the same size, although thickness-wise it is thicker. Now it is in a little rubber bumper case here, which we can pop off if we so desire. It's a typical silicone case, so grippy but soft. So probably will get dirty, but because it's silicone, it should be cleanable. So let's look at what else is inside here. We have an oscilloscope probe, and it claims 100 megahertz times 10 or times 1. I doubt that. It's got probe compensation, so that's kind of nice. And I think it was on the AliExpress listing that it listed this thing as 120 megahertz bandwidth. Yeah, I'm sure. On the actual scope, we have the single inputs, just one channel. We have a frequency generator for outputs, good for probe compensation. It is adjustable. I think it's just a square wave. It's not an arbitrary generator. On the bottom, USB Type-C for charging. That's nice. There's a charging LED spot there. And there is a 3.5 millimeter jack, which we'll get to in just a second. Also included here is this cable. And yes, what this is this plugs into the 3.5 jack there. And this actually has video output, as in NTSC video output. So this little screen here, which is quite small, obviously, if we go back to the cartridge there as a comparison, I will be able to actually capture the video output, I'm assuming, on the retro tank, so we can actually see what I'm doing with this little scope. That's a different change from the normal Handtech or whatever that I've shown on the channel before. That thing has no ability for any video output. All right, we also have this. I don't know what this is. I'll zoom up there. Kobao, and it's just in Chinese. And kind of wondering if this is like a free gift or something that was included with this. Okay, it's sticky. Is this one of those things you put on the back of your phone? So you can like, yes, I think that's exactly what this is. I wonder what these little, oh no, these aren't drill bits. These go in here. They're like tiny little jacks. So I guess you can make a cable for yourself if you want. They're like little mini banana jacks, like that. Okay. And then this is for putting on the back. So let's check that out. So I guess you're supposed to like stick this on here, like with an adhesive, and then it can stick through the back. You know what? That actually seems kind of neat. It's not stuck on yet because it will act as a little bit of a tilting bail almost. So I'm gonna stick this on. That's kind of cool. Yeah, it tilts it up. Okay, I like that. I'll just use a little bit of alcohol here to clean under here. Get my fingerprints off of there, or oil or whatever. We'll just peel this off so we get the adhesive. This thing will probably never come off. And how do I do this? There we go. Oh, it actually turns as well. Okay. Yeah, I like it. I'm assuming this blue label here comes off, which has writing on it. It does. All right, there it is. It's a little tilting bail indeed. So you can actually adjust the angle that this thing goes by just turning this around. So it's like more tilted there. And there, it stands up pretty well. Yeah, okay. Cute. That's pretty cool. All right, back to the unboxing, so to speak. Let's take a gander at the manual, which I'm sure is not written in the best English. There it is, the DSO1511G handheld oscilloscope user manual. All right, there's a section here on probe compensation. It just tells you how to do it. That's nice. It says here that in 1X, the probe is only 5 megahertz, which is pretty typical. It says if measuring more than 80 volts peak to peak, make sure you use the 10X setting, which is kind of a given. That's actually pretty surprising if the input on this thing can withstand 80 volts peak to peak or even 50 volts peak to peak on 1X. That's pretty surprising. Looks like you can save screenshots and then review the images. All right, here's the signal generator. It says it's actually good for a sine wave of 2 megahertz and other waves also 2 megahertz. And then here's the section on the video output. You have to go into the menu, go to set, and then long press run stop to enable video output. Disable if executed again. So, okay, pretty simple. I didn't realize that the USB-C connector actually is data as well, so you can copy the screenshots onto your computer. Under triggering here, it looks like it does rising, falling edge triggering, and that's probably it. It does seem to support roll mode, which is a nice feature for such a cheap little scope. Looks like it has auto calibration and fast Fourier transform functions built in. And then here are the specs. 120 megahertz bandwidth, sampling rate, 500 megasamples per second. These are extremely unbelievable numbers here. 128 kilobit sample depth, so that's not very deep, but I mean, for something that's 56 bucks, I guess. It says here max voltage is 40 volts peak to peak on 1X, which is what it said earlier in the manual. That's 80 volts there, AC that is. We'll take a look to see if this thing supports 100X probes, and if it does, then theoretically it would actually be good for up to 4,000 volts. I mean, not really recommended with something like this, but if you're testing that kind of voltage and you're not touching it while you're doing it, might be okay. Let's use this little probe that they give us, the supposed 100 megahertz probe. I don't know, we shouldn't need to connect that, but let's anyways, and we'll do the probe compensation first. All right, hopefully I'm not gonna get glare. We'll plug this into the RetroTink in a second so we can take a look at the output, or input that is. Oh, hey, it's got a little beeper. There it is. So it booted up very quickly, as you saw, just like a couple seconds. Holding down run stop brought the generator up. All right, so we're looking for a 1 kilohertz square wave. How do I get to square? Let's see, that changes that. Do I hold down run stop? Nope. As we can see, there's the signal. How do I get to it? Let's see. Pretty responsive. Okay, that moves the buffer around. We're looking around the capture buffer. And then we have volts and millivolts. I'm assuming volts increases it. There it is. Oh, and it's triggering. Nice. I think I have the probe in 10x mode. So let's go in the menu and look for the probe. There it is. Look, probe 1x, 10x, or 100x. So it does support 100x. Okay, that's pretty cool. All right, let me stop myself here. Let's hook up the video capture to this thing and get the video output so you can see it a little more clearly than me just recording the screen here. All right, so it's outputting composite video right now, but it just says ZEEWEII, which I guess is the brand name. So it told us to go into the menu, and we go to Set, and then we hold down Run Stop, and that should switch on the video output. Hey, there it is. Look at that. Okay, that's pretty cool, actually. It's not super high resolution, but I'm pretty shocked for something that's $56. I mean, it's updating quickly. It's not terrible. Wow, I'm kind of shocked. Okay, so the user interface is a little strange. You hit menu, and to change tabs, you push up and down, and that changes through the tabs. And then to move through the items in the tabs, you push left and right. You see how that box around the coupling and around the probe box is changing? And then I think what we do is when we're on here, we must push OK. Okay, and that switches it. It's a little unusual. It'd be nice if you used left and right to go through the tabs, and if you were on the tab you want to push down, and then you could select through all the items that were in there, and then you just go back up to the tab to then move left and right. It's a bit unusual that way, but I guess you can get used to this. All right, so the first tab is channel 1. There's only one channel on here, so that's pretty simple. Here's the measurement tab, and we can already see it's measuring frequency and peak to peak and mean. That's what we have at the bottom here, and I'm assuming we can only get 3 at a time. Oops, that exited out. That was my fault. Push OK. Oh no, you can actually have more stuff. Well, that's pretty neat. In fact, if we just go to all, it turns them all on and turns, okay, well, all actually doesn't turn them all off. You have to manually deselect them. I'm gonna leave it like this: frequency, peak to peak, and max. That's pretty much typically what I use the most. So now we're gonna switch to the next tab. There we have the trigger mode. We have auto and normal. Guess there's no single shot. So that's a bit of a limitation. Okay, it actually does say it has a single shot mode. So it's, I guess, somewhere else in here. We'll find that in a second. All right, so talking about these trigger modes, auto is just running all the time. Normal means it's only gonna show waveform while it's actually triggering, which means as soon as the trigger stops, then the waveform update stops. That's a useful mode depending on the situation. We have rise and fall trigger types, and then we can do auto or manual trigger level. I'm gonna set that to manual because I just don't like the idea of it changing it on its own, I guess. Moving on, we have some persistence here. Let's turn on some persistence. This is usually kind of fake. And like if I unplug the probe here, yeah, so it sort of fades away. That's kind of interesting. You can kind of see what it's doing in the background, right? Let's get rid of the menu there. Look at that. So that type of persistence can be useful if you have like a little glitch, and if this thing actually picks the glitch up, then it will stay there. And I think if we go back to the menu, there's an infinity setting, which just means it will never actually go away. That's where you can set up also the roll mode, so that's kind of nice. And then the brightness, which is already set to max. And to be honest, the screen is completely readable and no problems with the brightness. And the viewing angle is quite good. I'm looking at it at an extreme angle, so it's still visible in the camera, and it looks completely good. It's not washed out or anything. All right, here we are on the aux tab. So there's the calibration stuff. Remove probe first. I won't even run that. And then we have some FFT stuff. So let's, music, okay. Let's turn that on. Oh, it's actually gonna be doing like level bars. Okay, that's kind of cool. The FFT on this is basically gonna do a spectrum analysis. You can see it's kind of running kind of slow, but that's typical. And then here we have the last tab. We have auto shutdown on or off. It's currently off. We have sound on or off, and then the language. So yeah. Now notice there was nothing about single shot anywhere. Well, I remember in here, I think there's a button here. This power button says X key, and we hold that down. No, that turns it off. We push it. Oh, there we go. Okay, so that pops up another menu. And then we have single. So I'm gonna turn that on. Okay, and you see up in the top corner there, it says wait. Now it should single shot as soon as I just touch the probe here. There it is. So we get a little bit of a capture there, and then it says stop. So that works. That's kind of cool. It's weird that that's not in the trigger menu, but I guess they wanted it to be quickly accessible, hence this like X key thing here. Now let's see if we can click on this again to go back to the normal mode. Nope, that just did another single shot, and let's just do it again. There it is. There's the single shot. Now I was gonna demonstrate scrolling through the waveform that it captured, and it didn't really capture very much. It like captured one screen full, which is not very good at all. Okay. Now, how do we get this thing back to normal mode? Oh, we just hit run stop, and then now it's back in typical mode. Cool. All right, so you see that little arrow on the right side, just above the yellow line? That's the trigger point. And the interesting thing is, when I touch this, it sort of runs without being triggered for a little while, and then it triggers. So I'm not 100% sure what the deal is with that. It shouldn't be that slow, but it's possible this thing is using a software trigger. I'm not totally sure. All right, so there we go. So now it's in roll mode. It went into roll mode automatically, but this might give you the idea that we're looking at an incredibly slow waveform. We're not. This is just aliasing. So let's see if we push auto, if it gets out of this. Okay, yeah, it did. Cool. Let me try to change this waveform to a square wave. Let's bring up the frequency generator. I think run stop. I looked in the manual here, and you use these millivolt and volts button here to switch the waveform. Okay, we have noise, we have something, we have the top half of a sine wave. Well, it's almost like a rectified sine wave. We have a sine wave that has the bottom part chopped off, so that would be like as if you put it through a diode. We have a sawtooth wave, triangle wave, there's the square wave, and back to sine wave. Okay, cool. So let me try to do the probe compensation here. I have a little tool. It's a bit hard to turn the adjustment. You just need a very small flat blade, but yeah, that looks good enough. I mean, this thing is not super accurate, so like, what are you gonna expect out of it? Well, just for fun, let's switch it to 1 megahertz. Let's switch it to 2 megahertz. Let's max this thing out. Okay, it looks like we got some serious aliasing going on. Let's try the auto button here. All right, there we go. So we're looking at a 2 megahertz signal there, and it's triggering properly. It's a lot better than like that software-based USB hand tech, which barely triggers properly. So, okay, so I have to say, I'm actually pleasantly surprised by this scope at the price this thing is, and the fact that it has video output. I'm pretty amazed, actually. It seems to work pretty well, at least off its internal signal generator. So I think the real test now is, let's grab this broken 64. I was gonna start with the working one, but let's just go right to the broken one. And let's start looking at signals. And let's see if I can get to the bottom of what's wrong with this thing with this little oscilloscope. All right, so here we are. So this is one of the broken machines that I've been working on, like as part of this repair-a-thon. I know it's been a few months. Now, the sticker on here says number 4, but this is actually machine number 5, which has a black screen with a white line. So that means that the VIC is actually generating some output. What happened to number 4, you ask? Well, Roman, who runs the channel Epictronics, and sorry I put a space there, Roman, he actually was visiting the Pacific Northwest and asked me if he could come by just to meet me. And I said, yeah, of course. I was around that day. So he came down, and while he was here, I asked if he had any NTSC Commodore 64s because he lives in Europe, and he didn't. So we went through the pile of 64s that I had here to be repaired, and he grabbed a couple of them. So he's gonna have repairs on his channel. I'll link to his channel down below. I don't know when he's gonna do the repairs, but he will have repairs. And yeah, I think it would be kind of cool for him to have some NTSC 64s and you know, repairs on other channels. So that's what happened to the 4th machine, and there is another one we picked. I don't remember which one it was. Randomly, we took it out of the stack. I think there's up to 13 or 12 machines there that are bad. So yes, okay, let's crack this open. It is not unscrewed. Ooh, look how nice the bottom looks, and the top is very yellowed. The sticker here has some kind of odd mottled appearance. Not sure what that's all about. There appears to be one screw that is just spinning freely, and the other 2 are already missing, which implies that the standoff is broken. Oh, there we go. And I'm gonna say that someone has probably been in this thing before, judging by the fact that that has been ripped off. And there it is, the broken machine. It is our familiar friend, the 25407 motherboard layout. And I'm noticing there is not a single chip in a socket. That's pretty ridiculous. The PLA is often not in a socket, but the SID's almost always in a socket. This is a rare thing. I've had a couple come through before that were socketless as well. So it's not unheard of, but if you're a novice and you're trying to repair your machine and this is what's going on in here, it's very unhelpful. Okay, motherboard is out. There's the bad shield. We'll get rid of that. Ouch. Looking at the bottom here, sorry about the glare. We have some rust in the corners. So this machine obviously has been exposed to a little bit of moisture. And then looking at the top cover here, all the hinges are there. These standoffs are fine. This one is actually broken, but it probably still works with a long screw, and it has snapped off here. I think with a little bit of acetone thing, I could probably get that back on. All right, so one negative about this little oscilloscope here is it is using the composite video input on my RetroTink here. So I can't easily have both that up and also the 64, because currently I only have one RetroTink actually hooked up. You know what? I have another RetroTink, my old one, and I have a multi-HDMI capture card now in this machine, so I can plug both in. Let me get that set up. So the oscilloscope is currently being captured through the RetroTink down here, which is what you see right now. And if I switch this, now we're looking at the video output from this Commodore 64 going through my old RetroTink. So let's turn this thing on. No signal. Okay, there we go. So we have a black screen with the line. So that's interesting that that no signal thing popped up. I hadn't seen that yet. That's something on the capture card, I guess. But yes, it's kind of cool. I can just switch back and forth between the 64 and the little oscilloscope. So let's take a look at some of the signals on this machine. So this thing is set up, I think I was looking at the 2 megahertz signal, which is actually appropriate. Let's start with the clock signal. I have the probe clipped onto this, which is ground. On my phone, here's the pinout for the processor. So the reset line is pin 40, and we want to check that, right? So I'm going to hold that on there, and I'm going to power cycle the computer, and it should stay low for a second when we turn it on, and then go high. And it does exactly that. So we know reset is working perfectly. We're looking at Phi 2 output, which should be the 1 megahertz, and that's looking good. And then we have pin 1, which is the 1 megahertz clock input. This is actually what's coming directly from the VIC-2. The Phi 2 is actually generated by the CPU, which is why it looks a little bit different. All right, so the first pin we're looking at is data line 0. Let's zoom out a little bit on this. So I like how you can zoom in and out very easily without having to go into a menu or anything. To be honest, the Handtech portable scope I have is harder to use from a UI perspective than this. So right now what we're looking at, I'm turning the machine off and on, is just typical activity on the CPU. I'm looking for anything that looks stuck, like if one of these was just low all the time or high all the time, that could be something that's shorting that line high or low. Now what's interesting about this scope is it seems to have persistence, even when I have no persistence set at all. If I come on and off the pin, we can get a glimpse at what actually is going by, but it's harder to tell once it's running at full speed like this. So I don't totally love that. Still though, things look okay on the data lines. Nothing looks out of the ordinary. I think I'm on the last one there. Let's take a look at the address line. So here we are on address line 14. Now you see that kind of weird slopey thing there? Again, it's, I don't know, it's kind of hard to tell here what's happening. Let's adjust the trigger, which I'm not exactly sure how to do. Do I hold this button down? Pushing up or down moves the entire waveform up or down, and left and right moves your view through the 128 kilobit buffer. Okay, take a look at this. So there are actual second functions where I guess you hold down a button and push another one. So power plus up and down actually moves the trigger level. Oh, there we go. Right, cool. All right, so moving the trigger down helps. Now we're actually looking at exactly what I wanted to see. So that weird rise there is actually okay. That's a pull-up resistor, I'm pretty sure. And when the bus floats, it slowly pulls it up, which is why we're seeing that slope. And I think it's on only the high address lines. So that was address line 14, and this is address line 15. And this looks a little strange. So first off, we're only seeing 3 volts maximum on here, but then we're also seeing that 2 volts in the middle, and a pull-up resistor should pull it all the way up to, 5 volts or thereabouts. So this whole 2 volt thing is weird. I'm gonna power cycle the power. Yeah, this is very suspect. I don't think this is right. So if we take a look at the address lines, we're on 13. That looks completely normal. 12, 11, 9, 8, 7. I think we're on 6, and it looks a little weird. Let me go up here. Certainly is like a lot of undershoot there. See how it's dropping way down below? Interesting. I wonder what that's all about. I guess it's kind of normal. I don't know what, I think I'm on like 5, maybe 4, 3. Oh, do you see that how it kind of came into focus? That was because there's a bit of oxidation and I wasn't pushing hard enough. That looks good. 2, I think we're on 0 or 1. No, that's 0. Now we're on 0. And the next one is VCC. So that's just 5 volts. So all of the address lines are looking fine, except for 15. That's 14, and there it is, 15. All right, here's the schematics here. So let's take a look. So we have address lines here, and they're kind of multiplexed up here. Oh, you know what? Look, it only goes up to A13. A15 is not in play. On the second page, here is A15. Let's take a look at where this goes. So it's not there. It's not on any of those ICs. Let's go back to the other page. So there it is. There's the address lines they come in. It doesn't go to the ROMs. They are not, definitely not on those address lines. But if we go back here, it also goes up here, and look at this. There it is on U13, one of these multiplexers. So it goes into these, and then what comes out is the MH lines, which are the multiplex address lines that are going to the DRAM. So U13. So right there is U15. Now, if you've seen videos of mine before, often those chips, not often, but sometimes those chips are MOS replacement parts. They're always a 74LS257, but the MOS version is notoriously crappy and goes bad and then takes out the whole system, or you get garbage on screen, stuff like that. It's still possible though that this Motorola chip has failed on that address line. It's an input into this chip, right? It should never be actually doing anything to it, but maybe there's something failed in that chip and it's holding it there at whatever the 2 volts we were seeing. If I turn the computer back on, I'm just gonna see if it gets extra hot. There's another one right down here. Let's just see if it's warm. It's not warm, but let's take a look at pin 11, and there we go. We're seeing that weird signal. So what I'm gonna do, I think, is clip the leg, the pin 11 leg on this mux here, and let's take a look on the CPU and see if that cleans up this particular signal. But actually, before I do that, let's just take a look and see where else A15 is used. Because, oh, it's also used on the PLA. Of course it would be. So the PLA could also be bad. Now it also goes to like the cartridge port. That's what this is down here. Well, nothing is plugged in there, so that's clearly not the problem. I don't think it's necessarily used anywhere else. Just quickly taking a look here. Yeah, I really think it's just, yeah, it's not on the VIC. It's the PLA, and it's on that particular mux right here. So which one is it? Neither of these are in sockets, so it could be either one. Now, what's more likely to fail? The PLA is more likely to fail, unfortunately. So I think I'm gonna cut the leg to the PLA and not to this mux. And if nothing changes after cutting the PLA leg, then I'll reconnect it and then I'll cut the leg to this mux, and then we'll see what happens. All right, there we are. I'm on pin 4 on the PLA right now. And I'm going to cut the power on the machine, and I'm gonna snip with these cutters here. Alrighty, I think it's done. So let's take a look at this pin on the PLA. Okay, it's doing nothing. So let's take a look on the underside. Well, would you look at that? That signal, let's go to the CPU on address line 15. That signal now looks normal. So I think that PLA has failed. Now I can use this little tool here and I can try to short the leg, and we can see it. There we go. I've reconnected the PLA leg and I've disconnected it. That is not normal. So I think that pretty much confirms that this PLA right here is a goner. So time to take that out, and then we'll pop in one of the modern replacements, and this should fix the machine, maybe. Or there's another fault. I guess we'll find out. All right, jump cut later. The PLA is replaced. There it is. I took it out. I actually added a pin back onto there so we can test this in the socket. Socket is installed, and we hadn't yet looked at the backside of the board because, of course, I had the RF shield on there, which I have since removed. The back of the board looked good. There was quite a bit of flux residue on the hand soldered parts on here, so I actually cleaned that off with a toothbrush while I was cleaning up the work I had done on the socket here. Now I'm gonna say that this board has actually had a little bit of rework done down in this section. It was probably done during a QA process after the wave soldering that put most of the parts on this board. Someone probably just went over this part by hand because it wasn't quite done properly. Definitely it's not all the pins. So I think that these chips down here are likely original. Notice that the RAM chips don't match, but that was pretty typical for Commodore back in the day. All right, so with the machine on, let's look at what is A15. I think that's it right there. Doesn't seem to be doing anything. Let me power cycle it. Of course, with the PLA not in there, yeah, machine's gonna do strange things. But at least we're seeing a good 5 volts. I'm gonna say that that address line is now working fine. I mean, we kind of validated that was the case by cutting the leg off of this PLA. All right, let's go into here where I have some replacements. We're gonna use this one, the PLA Advanced. Okay, there it is in the board, nice and easy. Let's turn this on and I'm gonna switch this over to the video input and look at that. It freaking works. That was it, yeah, so definitely a bad PLA chip. And I'm pretty pleased with what we saw with this little oscilloscope there. It led us right to the problem. Well, of course, it led us to the PLA being bad or one of the MUX chips, but I took a guess that it was the PLA, cut that leg, and then the line returned to normal, and then there we go. Now, I have mentioned this before, that I feel that these cheap oscilloscopes have a really good purpose, and this one being super inexpensive really competes with a logic probe when it comes to diagnosing a system. Now, logic probes have audio cues on them, so you can very quickly go down a row of pins and hear if they're low or high or pulsing. But the thing is, I'm pretty sure a logic probe, if we had touched that pin that was on this bad PLA here, it would have just showed pulsing. But we needed to actually visually see that the signal wasn't good to know that basically there was a problem with that signal there. Now, of course, if you're not familiar with how the Commodore 64 looks, you might be tripped up by, say, that pull-up resistor, which is that curving trace we saw. The thing is, though, that one address line did not look like all the others. And when you see stuff that's like 2 volts, 2.5 volts on TTL, and it's not going higher than that, that's a red flag right there. And that's where the oscilloscope comes in really handy to give us an idea that there's actually a problem there. Before I plug the diagnostic test harness in, I want to see what a higher clock signal looks like on this cheap oscilloscope. Remember how it said it was good for 120 megahertz, which I totally don't believe. Let's go on to the VIC chip on pin 21, and we should be seeing like the output of this crystal oscillator right here, which it actually is counting as 14.3 megahertz. Why don't we try the auto function on here? Let's see what this does. Oh, there it is. So it's actually showing 14.2 megahertz, and the waveform shape, which is a square wave going into this, it looks okay. Notice how it only says 14.4 or 14.3 megahertz. So there's not enough digits on this particular meter to be able to adjust a crystal oscillator exact frequency using the variable capacitor that's on the board here. But it's definitely working, and let's check out pin 22, which is 8.0 or so. It should be, I think, about 8 point something megahertz. And yeah, that signal, of course, looks good as well, since, of course, it's even lower frequency than the other one. I'm honestly a bit shocked that this thing can actually measure frequencies more than a few megahertz. Okay, back to the machine. Let's do some diagnostics on this thing. Let's see what works and what doesn't. So, Easy Flash 3 cartridge, and we'll run some diagnostics on this thing. I have a couple diagnostic images on here. We'll just run one of these. We'll let it run through. And hopefully there's sound. Let me turn the speakers up. Oh, there won't be any sound because it's not actually connected to the speakers. Let me just do that while this is testing. All right, I missed it. There it is. All right, so the SID appears to be actually working. That's surprising as well. All right, here we go. This is Sven Petersen's new updated test harness. This is the one the viewer sent in that actually works because my last one was misbehaving. All right, let's turn this on. I'm gonna use the joystick and then I'll swap to the last cable here. Whoa, it did not load. Why? That is interesting. The Easy Flash doesn't work. I've never tested this actually. Easy Flash doesn't appear to work while the harness is connected. I am also noticing And my Easy Flash seems to have a loose part inside. I wonder what happened there. We'll just grab this. So we have dead test and we have the regular diagnostic on this cartridge. All right, there we go. Let's turn this on. The Elgato capture device there takes a little bit longer to actually start and show a video signal than the other one. So that's a bit unusual. While this runs, let's pop the cover off here. Let's see what's happening inside of this. Oh, what's loose? What's loose in here? So there it is. It appears that an LED came off. Okay. This machine appears to be fully functional. I see it, yeah, everything passed. Okay, cool. This LED doesn't look like it was ever actually soldered in. It was just placed into the holes there. No, it actually was soldered on. It just broke off over time. Okay, no problem. I can fix that. I gotta say, I've never opened my Easy Flash. Look at the contacts there. They are worn. Wow, it's the good quality contacts, ENG, I think it's called. Some kind of electroplated gold, but that is, yeah, ouch. I went ahead and I soldered on a new LED. The problem is that this whole board moves around in the case. So if we put it through here like that, basically every time you insert it, it jiggles around a little bit, and the LED, which is in that hole there, the legs get stressed out. So it breaks off basically. Ideally, the way this should work is there should be a surface mount LED and then a little plastic light pipe thing that's on top of it that could slide around a little bit to give that give as you put this in and out of the computer. Next, for the contacts, what I like to do to clean these is actually a little piece of magic eraser and a little bit of Deoxit. So I'm just gonna put some Deoxit right here along the top. And I'm gonna take my little tiny piece of magic eraser, and I'm just going to wipe it like that. Look at the filth that just came off. Let's do the backside. Same thing, we'll just put a strip of it. Grab the magic eraser, let's use the other side there. Look at that, pretty dirty. I know people talk about using an actual pencil eraser, but this magic eraser stuff really works well for me. And of course, everyone knows what time it is. We cannot have an actual 64 repair video without it. There we go. I don't know if you could see that, but I put a pink light inside there, a little pink LED, because, you know, why not? Red's kind of boring, so pink, a little more exciting. Go down to Adrian's tools, and there it is, 8-bit dance party. Plus we'll validate if the SID sounds good. Ah, it doesn't sound good. Okay, let me connect the audio into the capture device here so you can hear it with a direct capture. The 64 is now plugged directly into the HDMI capture device. I'm actually back on my other RetroTink as well, so the video might look a little sharper because on the old one I was just using the composite video. When I start the 8-bit dance party, just take a listen to the beginning especially. It just sounds like some of the notes are actually missing. All right, well, that's kind of interesting actually, because while the beginning sounds a little weird, the rest of it actually sounds totally fine. So the SID is only marginally not working properly, and a lot of people might not even notice that it sounds just ever so slightly off. So I'm actually not gonna take this out of the board. I'm gonna say that this is probably good enough to use. Let me switch over to the Kung Fu Flash. I have a SID player on there, and I just want to listen to a couple other SIDs, and I'll try to identify if any of those sound weird as well. Alrighty, there we have it. That is one repaired Commodore 64 board. It just had a bad PLA. Turns out that the SID, if it is slightly not perfect, it sounds pretty much perfect in all the songs I played. We have to remember that the SID chip is actually an analog synthesizer, an analog digital synthesizer, and there is variance from chip to chip just because those filters and stuff are analog. So it's possible that this one just doesn't work exactly like I expect it to. The SID chip that I'm used to listening to all the time is the one that's in my ZIF machine, which is a 6581 AR4, which is just one of the later versions, and it just sounds slightly different than these earlier ones. But anyhow, in the end, all that was wrong with this thing was a bad PLA, which people are going to say, not surprised. But again, the intent with my videos is to show you that you can actually identify that it is a bad PLA before you just go removing chips from the board, which always brings a slight risk of damage, especially if you're not super familiar with how to desolder stuff. I took the opportunity on this video while repairing this to test out this little oscilloscope, which of course I have on the little finger ring thing here. And I gotta say, I'm mighty impressed by this little thing. It's not gonna be 120 megahertz like it claims. I mean, I only tested up to 14 megahertz, which is what's available on the 64. But for repairing 8-bit machines, this thing really does work well. And look, let's compare it again to the Easy Flash cartridge. They're basically the same size. The oscilloscope is just about twice as thick, but look at that. It's pretty amazing that something so inexpensive can actually be pretty useful. Comes with a probe. I mean, yeah, I'm mighty impressed by this. So if you are looking for a really inexpensive oscilloscope to help troubleshoot machines like Commodore 64s, I gotta say, this thing really fits the bill. And if, like me, you have bad eyesight, well, you can plug this thing into a monitor and then you just get a larger thing. Roll up a large television set to your bench and this thing will do that too. That's pretty cool. So anyhow, I think that's going to be it for this video. I hope you enjoyed the repair of this Commodore 64 and you saw one of the various failure modes of the PLA chip. And I hope you enjoyed my little review of this. I actually have another cheap oscilloscope that I ordered that I'll do on the next 64 repair. I think it's kind of fun to repair these with these cheap scopes and just to see if this can actually work. Anyhow, I think I've talked long enough about that. If you enjoyed this video, I would appreciate a thumbs up, but if you didn't, you know what to do. I want to thank my patrons. Their names are scrolling up the side of the screen. They get early access to videos, and the higher tiers also get behind the scenes special footage. I put videos and pictures and other things up on there about stuff that's going on here in the digital basement. So if you're interested to know more about like what I did with my new bench PC up there, then it's my higher tier patrons that was able to see the behind the scenes videos, me talking about that machine and plus how I edit videos and other stuff like that. So that's gonna be that. Hit subscribe if you haven't already, I really appreciate it, and comment down below, and yeah, that's gonna be that. Stay healthy, stay safe. I will see you next time. Bye-bye. We have a little bonus footage at the end here. I meant to do this in the video, but I didn't. So here's the oscilloscope connected to my 1084. And right now, one of the problems is it is not in color. And that means that this thing outputs in PAL mode. Now I have the camera set for 1/50th of a second. Otherwise we'd be getting a bunch of flicker, but my North American monitor here does not have the capability of decoding PAL color. No matter what the setting is on the back of the monitor, it is in monochrome. So that is one negative. It was capturing perfectly on the retro tank because it has no trouble decoding PAL, but it's too bad there's no NTSC setting for this, but I guess it kind of makes sense. So that means that you have a little bit of a limitation on where you can use this. Obviously a monochrome monitor, like a little Apple monitor or something like that would work fine. This boxy Philips brand 1084 has no trouble synchronizing to a 50 hertz signal. It just can't decode the color. So you're gonna get monochrome and you're gonna get a little bit of flicker. So keep that in mind if you're buying that. I'll have to put a little note in the video that it's not NTSC color, that it's PAL.